Welcome to the ET302 Logic Gate lab presentation. Here I show two logic probes. Okay, we have VCC, we have a load resistor, and an LED and an LED. And this is designed if I put in logic 0, which is ground, that the green LED goes on, meaning logic 0. If I put a high in here, meaning 5 volts, that the lower LED will light, the red one, meaning a logic level 1. And we're going to use this in order to analyze the gates. Here I have two AND gate logic circuits. Still we're using our logic probe. And here we show the IC view. It is VCC on pin 14 and ground on pin 7, which is typical for TTL chips. 7408. Here I have an SBDT, single pole double throw switches that I could put in VCC or ground, logic level high 1 or logic level 0 low. And I have two of them, one for A and one for B. And what I've done is I've matched the circuit and I use the gate view. And there are 4 gates in this 8-pin LED. And I've connected this one, same logic switches, and they should operate at the same time. Here I have the operating multi-sim circuit here. And here's our logic probe, and here's our inputs. When the lights are off, it's 0. When the light goes on, the little probe, it's a 1. So we're going to go through the truth table here. So 0, 0 equals 0. So let's try 0, 1. 0, 1, and our output is still logic 0. So now if I go 1, 0, it's still a logic 0. So if I go 1, 1, it's going to be a logic 1. So an AND gate, if both are true, the output is true. Here's a symbol for an AND gate. And here's our truth table. So A, B, and output X, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. So if both are true, the output is true. Here's our multi-sim circuit for OR gates. We have the IC one here and the logic gate one here. Again, we have our logic probe and our input switches. Off is low and on will be lit. Here's a working multi-sim circuit of our OR gates. We have 0, 0 equals logic 0. 0, 1, 0, 1 is going to be logic 1. 1, 0 is also going to be logic 1, and 1, 1 is also logic 1. Here's a symbol for an OR gate, and our truth table, 0, 0 equals 0, 0, 1 equals 1, 1, 0, 1, 1, 1 equals 1. So essentially, if either of these two or both are 1s, the output's going to be a 1. Here we have a multi-sim circuit of an inverter, a NOT logic. So again, we have logic probes. We have one switch here because there's only one input. And we have our logic diagram for a gate symbol right here. Here's our inverter schematic in multi-sim. Here we have the IC again. VCC goes to 14, 7 goes to pin 7, and we have our logic probe. And whatever we put into an inverter gets complemented, gets opposite. So here we have 0 in, we're going to get a logic out. Here we have a 1 in, and we're going to get a logic 0 out. Here's our inverter logic symbol and our truth table. So anything goes in, if 0's in, 1 comes out. If 1 goes in, 0 comes out. Here's a circuit where we're combining an AND and an inverter. And what we're doing is we're creating a NAND gate. And NAND would be an inverted AND. So we have a NAND and the inverter goes on the front end. So whatever comes out of our AND gets inverted. Again, we have our logic probes. Here's our combinational circuit for a NAND gate. And as we see, if we have a 0, 0, we're going to get a high out. And if we have a 0, 1, we're going to get a high out. If we have a 1, 0, we're going to get a high out. And if we have 1, 1, we have a 0 at a low. So 1, 1 gets a 1 here, gets inverted to a 0. Here's our symbol and our truth table for NAND gate. As you see here, we have a symbol for an AND, and we have a bubble on the end. This bubble represents the inverter. So here's our truth table. 0, 0 is 1, 0, 1 is 1, 1, 0 is 1, and 1, 1 is 0. Here's our NAND gate circuits. Here's our IC again at 7400, 7400, a VCC at 14, and ground at 7. Logic probes and our NAND symbol. So let's go. We have 0, 0. We have a logic 1. 0, 1. We have a logic 1. 1, 0. We have a logic 1. 1, 1. We have a logic 0. The same as our combinational circuit. Here's our logic design circuit for a home alarm. And what we have, it said 3 windows and 3 doors, or excuse me, 1 door. And what we want to do is, if any window and the door, if any of these are tampered with, or any combination of these or all of them, we're going to get alarm. And that's perfect for an OR gate. So if either one of these windows or both, then we're going to get a signal. So if our window or door is tampered with or both, it's going into an OR gate. So this is going to produce a high 1. Alright, so if either one of these pairs has a problem, this one is going to go through. Here, this is a control gate. And what we've done is, for a logic circuit, we need to turn this circuit on and off, and we use a control gate. And what we're going to do is we're going to put a logic signal in order to have the control gate allow the pass the signal. And here we have a probe just to represent the beacon. So let's break window 1 and turn on our alarm. And we're going to get alarm. So let's fix window A, and let's break window B, and let's break window C, and let's break door 1, and let's break a combination of all of them. And let's turn the alarm off to show that it actually works. So here we have a working circuit of a nice home alarm. Here's our home alarm, and I've added something fancy here. We're going to flash our beacon. And what I've done is I've added another control gate, and I put in a clock circuit. This is a function generator basically. And anytime that we get the alarm out, and we're going to input this signal, and we're going to flash the beacon. So let's go ahead and turn our alarm on. And let's just break one window. And you see it's flashing here, and it's flashing at 3 Hertz. So again, I could break all the windows. And again, it continues to work.